All right, so we are the TCNJ parking lot live web monitor. Our group consists of me, Caleb McKinney, Connor Dick, and Jonathan Brito. So this is our senior project demo. So basically, our project is pretty hardware intensive, and it consists of basically, sending information up to a website interface. And basically, what our project does is it counts how many available parking spaces are in a parking garage.
Chuck, I don't think we're getting any sound through.
Oh, really? So I guess I'll just play the video and explain it. Basically, we're testing nodes for voltage, and so this was like our testing phase. But yeah, this is just our prototype for our project, and basically we're just testing the hardware components. And this is testing to see that the sensor basically reads a car when it's coming into a lot. Okay, so here we go. So for our project description, like I said, like basically it's to track like cars going into a parking garage. And this is basically just the overview of the environment in which we're going to do our tests. It's our lot 5 of our college, or lot 4 of our college.
I'll do this one, Chuck.
All right.
So our first step was to make the overall like architecture and just make a block diagram. So that's what you see here. So there's several components. The biggest one being the Atmega 328P, which is the microcontroller we're using for all the embedded code to tell the sensors and the modem what to do. And we are utilizing 2 ultrasonic sensors and 2 PIR sensors, 1 PIR and 1 ultrasonic on the entrance, and then the same thing on the exit side. And because we don't have access to like power at the location where we're going to have this at the gates, we have to utilize a battery and solar panel so it can supply its own power and keep itself running constantly, so we don't ever have to worry about losing power.
Yeah, so that charging system is shown here. So essentially we're using a 12 volt, 10 watt solar panel. The voltage is stepped down to about 7.2 volts through a regulator, the LM2576. There's then a SLA battery charger implemented that is used to charge the battery in 3 separate stages. It helps to prevent overcharging of the battery and just protects the battery in general. And then this battery is connected to 2 different regulators. So the 5 volt regulator is used to power the microcontroller and the 2 sensors, and the 3.8 volt regulator is used to power the modem on our system.
So as I was saying before, we have 1 ultrasonic and 1 PIR sensor at the entrance, and the same thing at the exit. And the reason we use 2 was because, or 2 different types of sensors, I should say, is because if you rely on only 1, something could happen. There could be some like weird case where a car gets by and doesn't notice it, or a car gets by and like something happens where it'll count as 2 cars. So if you have 2 sensors, you could utilize sensor fusion to make sure that that doesn't happen and get like clear results, and make sure you know exactly how many cars are entering and leaving. This is a quick design of the breadboard I made for our testing. And as you can see in the center, the Atmega chip microcontroller is at, everything's really connected to that. And the modem is on the bottom right. The 2 powers are on the bottom left. And then the top left is the 2 ultrasonic sensors.
So these are just some preliminary calculations that we did to determine the charge time for the lead acid battery that we chose. The most important number is at the bottom of the screen. It says time charge for the 12 amp hour battery is about 19.2 hours. So next slide, Chuck. And then this is the discharge time for the battery. So you can see that the discharge time, accounting for all of the current that all of our loads are going to be using, including the sensors, the modem, etc., it's about 101 hours. And this is important because the discharge time is significantly higher than the charge time, meaning that the battery should always have enough power to supply the current needs for the loads that we're using. So there's a couple different chips that we're using for this. So we use the voltage regulator, the LM2576, in 3 different instances. The first is to go from 12 volts to about 7 volts, which is where we're going to be charging the battery at. And then the other 2 voltage step downs are from about 7 volts to the 5 volts and 7 volts to 3.8 volts. So the loads that we need are at 5 volts and 3.8 volts. The modem also has spikes of up to 2 amps that it consumes. So that's an important reason we chose the LM2576, because it can pass about 3 amps of current. The other chip that we're going to be using is the UC3906, which is a sealed lead acid battery charger. And as I mentioned before, it essentially is used to monitor the charging and discharging of the SLA battery to prevent overcharge protection. And it can effectively cut off charging whenever it senses the battery is reaching a very full state. So this is just the schematic for the LM2576. The most important part of this is the equation at the bottom. It says V out is equal to 1.23 times 1 plus R2 over R1. So with the voltage divider on the far right side where it says R2 and R1, that effectively can be used to determine the output of the regulator for any given input. And here is the UC2906 chip. The UC2906 and UC3906 are pretty much the same chip, just slight variation. So all the calculations on the side were used to determine the resistor values for this SLA battery charger. So this is what we're going to be implementing to monitor the battery charge and discharge.
So this is just the schematic, like Connor explained, of the UC3906. I basically just did this on Eagle. This is going to be an external attachment to our main PCB. So we're going to attach this with like a proto board. And then, yeah. And then in regards to the main PCB, this is the design of our microchip. And so we decided to use the Atmega 328. And there's a crystal oscillator on pins 9 and 10, and as well as the Adafruit programmer to program the chip directly on the main PCB. Now, this is our power system. Like Connor said, we have the LM2576. We have 3 of them, one for 5 volt regulation, one for 3.7 volt regulation, and one for 7 volt regulation. And then the battery and the UC3906 are connected up here. And then this is our modem subsystem and our sensor subsystem.
There's a picture I took the other day of the testing breadboard that I've made for the modem testing. So I just wanted to test the modem separately from all the other components. So I just used a Arduino board that I already had that uses the same microcontroller as the one we're using in our project. So it was just a lot easier just to test it like this and ensure it's working before integration with the other components.
And this is our PCB that I designed, and basically it's a 4-layer board, one for power, one for ground, and then 2 signaling layers. Yeah, and that's just my PCB design. And this is, we got it manufactured at JLC PCB, and this is what the final product looked like. And then basically, in order to like test it, I basically just mounted it to a piece of wood so that way everything would stay sturdy. And so we have our main board in the top and our external board at the bottom.
This is a flow diagram of the embedded code. And there's a lot going on here, so I'll just say very simply. The microcontroller, like you have to use a certain method to make sure that you are using the sensors and getting data, but also transmitting at the same time. And transmitting takes to the website takes quite a long time, up to 30 seconds in my testing. And you can't be sending data for 30 seconds because a car could come in at that point. So one solution is to utilize interrupts and have an interrupt go off every 100 milliseconds. And that uses the ultrasonic sensors, gets data from them every 100 milliseconds. And that leaves enough time in those, in the 1 second to send the data for the rest of the time. And then do an interrupt real quick, get the data from the ultrasonic, and then go back to sending the data to the website. So this will make sure the data is sent and however long the data takes to send, but it's still using the sensors to get the data. Now this was using that breadboard setup that was shown a few slides ago, using the Arduino to actually change the available cars on the website at parktcnj.com. And this is the response headers from the website showing that the HTTP GET request was successful.
So overall, this is like the integration of both like the web application and also the embedded software. So the user will have some access to a web browser or some other type of HTTP communication, and it will send a request to one of Azure's web servers. And from there, it will query the cloud database for the specific amount of spaces are available for Law 4. And then on the other side of the backend, the embedded software is going to be communicating with the cloud database, sending post data, manipulating how much spots are left. So whether a car left, it'll add up a space, or if a car arrived at the lot, it will take away a space. So it will be delivering real-time information to the users accessing the web app. So this is one of the desktop view of parktcnj.com. This is for, again, desktop view. So the user will be able to go to lot 4, lot 16, or lot 17. And from there, one of the APIs is designed to trigger a GET request. So that GET request will deliver real-time data to the user. And the response time is always less than 500 microseconds. Something to be considered real fast is from 50 to 150 microseconds, but since it's still considered to be less than 500 microseconds, it's still considered to be real-time data. And again, this is just another view of parktcnj.com on a mobile view. So just being user-friendly for both versions of this web application, something that we strive for.
So basically for our embedded software testing, we
I'll do this one, Chuck.
Okay, sorry.
So yeah, the what we've done on that initial test that was shown at the beginning of the presentation was that the upload to the board on the actual PCB was a success, and that the serial monitor gave the correct readings based on the algorithm that we had. And previous circuit was
Caleb, were you not finished with the previous slide, or are you having difficulties?
I was
Oh, it's because right now you're kind of cutting off. I'm not sure if you're having like good bandwidth.
oh sorry. I don't know if you can hear me.
We're getting by. So for the web app software testing, there's 3 things that we want to consider. So one of the main things is for designing a good API, its usability and maintainability. So with that regards, it will be with the health check endpoint. So we want to make sure that it's always available for the users to access. So what this health endpoint does is make sure that we're connected first to the web app and also making sure we're connecting to the database. So if any one of those fails, it lets us know by email, like every hour. We could have made it every 5 minutes, but we thought that was too extensive for the senior project. So it queries it every hour. And so far we had 100% health. So, and also for the monitoring endpoint, this is just to collect metrics of like the web application. So keep track of how many queries, the average response time, and also the usage for our virtual machine. So a classic example is if it wastes more than 75% of the VM, there will be another instance created to kind of route traffic to reduce the heavy usage.
So this is just, here, you can do it. So this is just our spending throughout the semester, and basically we've been on track to meet our 400 budget. Does anybody have any questions about our project?
We have time for like one question, then we got to get to the next group.
All right.
But
Yes, we are, Brock, we got your message. Yes, we are testing for obstructions and something like that. Each information that's being sent from the embedded software will have a unique serial number. So in case if that data wasn't transmitted or if the data is duplicated, the web application will have a different type of database that will keep track of these serial numbers and filter from there.